Hi, is the media microphone working? Can you check, Roji and Manjuriti?
I check. You can hear me, right?
Yes, I can hear you
Yes.
now.
Yeah.
Thank you.
Yeah. Maybe you should start, right? Okay. Surajit, maybe we'll start. So we are happy.
Okay, sure.
Yeah, we are happy to have Surajit from University of Warsaw. He'll be talking about new clues to Hubble tension using fast radio bursts. Okay. Yeah, you can start.
Okay. Okay, thank you for the introduction. And yes, in this today's talk, I will be talking about some different perspective of Hubble tension using the fast radio burst data. And this particular talk I have done in collaboration with some of the people here. Also, I'm a member of some scientific collaboration international group. So I'll talk about one of them at the end of my talk. So my talk is somewhat like it's a combination of theory, data analysis, and simulation. So you will get some perspective of every aspects in this way. So the plan of my talk is that I'll talk about some introduction of fast radio burst at the beginning. And then my focus will be mostly on how to estimate the Hubble constant from fast radio burst, and thereby also validate the validation of the cosmological model using machine learning as well as using standard Bayesian analysis. And if time permits, I'll later talk about some other aspects of fast radio burst, like how we can constrain some fundamental parameters like fine structure constant, proton to electron mass ratio, or also how we can discuss about its generation mechanism and thereby talking about the gravitational waves from it. And also some other constants like primordial mass black hole fraction made up of dark matter from fast radio burst lensing and future aspects. So let's start with the fast radio bursts. So what are these? So they are basically radio transient events. They are observed in the radio frequency band, and transients mean they observe for very short duration, typically of the order of millisecond. And so far, all the FRBs that have been observed, they are observed in 100 megahertz to 8 gigahertz frequency range. So there's a radio frequency range. And they are very bright in the radio sky, so their flux is of the order of Jansky. And so far, until today, that 854 FRBs have been reported, out of which, of course, majority of them by Chime telescope in Canada. Out of 854, 58 FRBs are observed to be repeating, but mostly not. And when I'm saying repeating, they are not periodic repetition, they are aperiodic in nature. And out of 854, 118 FRBs have been localized. That means their redshifts have been measured, and the maximum redshift that's measured like a few months ago up to slightly over 2. But there are some redshifts which also goes over 1, for a few FRBs. They are mostly extragalactic in origin. That means they are originated outside our Milky Way galaxy, except for one notable example, which discovered in 2020. But the general expectation rate, if we have full sky coverage and enough sensitivity, is about 100 to 1,000 per day. But we are yet to touch that limit. And lots of theories have been proposed to explain FRBs, and there is a nice website which collects lots of theories. So this is the first FRB that was discovered, also famously known as the Lorimer burst. So in all FRBs, there is one particular characteristic feature that's called dispersion sweep, which is this particular line, which says that different frequencies of these FRBs, so you can see the frequencies on the y-axis, arrive to the telescope at slightly different time. And this particular feature is known as the dispersion sweep. And because of this discovery, first three authors of this paper got the Shaw Prize 2 years ago. So let's talk about this dispersion sweep, because that's the most important feature of any FRBs. So I'm just showing one video here. Suppose there is an FRB originated outside our Milky Way galaxy. And if there is no hindrance of light by any particle along its way, all the frequencies of light should arrive to us at similar time. But suppose there are ionized plasma in the along the path of the light ray, so then we see some refraction of light effect, looking like refraction of light, and different frequencies arrive to us at different time. And because of this particular feature, in the previous slide I showed you the dispersion sweep. That phenomena is observed for all FRBs. So this is the schematic diagram of that. So the FRB is originated in some galaxy, and we are sitting here in the Milky Way galaxy. So what are the major contribution for this dispersion sweep? And generally, it's the quantified something called dispersion measure, which defines the electron density or electron column density along the line of sight. That means the electron density along this line. So what are the major components which can contribute to this dispersion measure? So of course, there can be host galaxy, whatever is coming from here. So it can contribute to this. And our Milky Way galaxies, plasma, ionized plasma, and its halos, they can also contribute. And also the other contribution comes from the intergalactic medium between both the galaxies. So majorly, we have these four components. So we have Milky Way, its halo contribution, the intergalactic medium contribution. Of course, this FRB can be at very far distance. So this contribution will be dependent on redshift. And the host contribution. Host contribution locally is independent of redshift because it's a local, the galaxy is small. But because this galaxy itself is redshifted to us, so we need to divide this as 1 plus the redshift factor of this galaxy. And of course, if you compute this delay of arrival time, so we observe that it goes as inverse square of the frequency. So now out of these four components, generally, of course, the DM contribution along the line of sight. So out of this four contribution, we generally have fair idea of the Milky Way, and it's mostly halos because these are local quantity to us. So these are some typical FRBs I just chose, and these are their observed dispersion measure in the last column. The unit is parsec per centimeter cube. And we have fair idea of dispersion measure from our galaxy along literally on all direction. And because of this, we can see that the observed dispersion measure is way higher than that can be produced from our Milky Way galaxy. So it's confirmed that this FRBs originated outside our Milky Way galaxy, and that's the confirmation that.
Hey, Surajit.
Yes.
So this Galaxy DM, you used any 2001 or YMW16, or you checked both? Because in some region, discrepancy is more than double,
Yes.
right?
So this I just choose from this website. So they calculated only any 2001, but of course this I chose little earlier because this website is down now. So they are no longer available. But generally, for other like if you go to Chime catalog, they generally give both the values.
Okay. Yeah, please go ahead.
Okay. Yeah. Thank you.
Sorry, one question. This
Yeah.
DM that you have 179 and so on, that's directly the electron number density, or is that something else?
So it's the electron number density integrated along the basically colon electron number density along the line of sight. So DM is basically the contribution. So you need to, of course, this is observed. So theoretically, I'll come how theoretically we can do that. But it's basically if something is at very far, so it's kind of integrating more and more.
So the units is per centimeter squared or what in that?
It should be per centimeter square, but in astrophysics, we generally write in parsec per centimeter cube. So that's a more natural unit, basically. So it's like how much parsec per centimeter cube.
And so that this number is in that units, is it?
Yes, yes.
Okay, all right. Thank you.
So, of course, as I said, large dispersion measure implies that sources are extragalactic. So now coming to a question, how this dispersion measure actually looks like. So of course, you can see out of Milky Way, halo and host, these are kind of local quantities, so they depend object to object. But this dispersion measure of IgM, we can in fact calculate this. So as I showed in the previous slide, dm IgM is proportional to Ne into dl. Now you just need to substitute what is Ne, so number density, which you can write in terms of baryon number density and other constants. And the distance L, that's basically the luminosity distance, but you can convert it to co-moving distance and thereby the cosmology. So once you substitute all of them, you can write basically the average dispersion measure for this IgM quantity turns out to be this particular factor, where this kind of Hz is the Hubble parameter, H0 is the Hubble constant, and those comes due to the DL contribution, and all other contributions like MP, all this FIGM, chi, so they comes from the Ne, basically the electron number density. So FIGM is called the baryon fraction in the IgM, and chi is the ionization fraction. So depending how what are the material present, so these numbers can vary. So this is a very fantastic relation and famously known as the Mackart relation also from the first author of this paper. And you can see out of all four quantities, only this IgM quantities explicitly contains all the cosmology here, like Hz and H0 here. So next, when I'm going to estimate, say, Hubble constant or other cosmology, I'm going to use this relation over and over again. And like this is the master equation to estimate cosmology from FRBs. So now I'm coming to that point. So before estimating, I'm just giving a brief introduction of Hubble constant, which we probably all know. That Hubble constant describes the rate of the universe expansion, and it appears as a proportionality constant once you solve the Friedmann equation. So it's the Hubble parameter that sits in the denominator in the Mackart relation can be expressed in terms of the Hubble constant and what model of cosmology we use. So if you're going to use Lambda CDM cosmology, so these factors will simplify as omega matter, omega lambda, combination of omega matter and omega lambda. But it can vary if you consider different equation of state. And so one important point that I'm going to use in the second half of my talk is that, see, left-hand side is more of a measured or observed quantity. But this right side, this exponential factor depends on the theoretical model that we predict. So naturally, this Hubble constant, which appears as a proportionality constant, it need not be a proportionality constant if your observation and theory do not match each other. So in the later half of my talk, I'll try to see if Lambda CDM, suppose I substitute Lambda CDM here, and my observation data, that means my FRB gives my left-hand side, can these two agree to the Lambda CDM cosmology or not? So that's in the later half of my talk that I'll try to prove. And current status of this Hubble constant is that from early universe data, we have, from Planck CMB data, we have roughly 67 kilometer per second per megaparsec, whereas late time universe data like SHOES from type 1a supernova gives slightly higher value of 73. And of course, they are in tension because the error bars also do not overlap each other. And a very recent review on this is the Cosmoverse paper, white paper, which gives all the different probes. So all the early universe, you can see they are coming at the low values, whereas the late time universe coming at the high value. And our paper contains this last one, that FRBs, that I'm going through now. So to estimate a Hubble constant from FRBs, we now...
Can I ask
yes.
one? Yeah, it's a basic question. I'm not sure how to
Sure.
ask this, but if we think of Z as a redshift,
Mm-hmm.
so now that is frequency dependent, right? I mean, now because of the
Yes.
dispersion.
Yes.
So what do we mean when we say Z? Now, not all frequencies have the same redshift, it looks like. But then the cosmology quantity, it is the same Z.
So
I don't know, my question makes sense, or
can you like tell me again in different ways. So one thing I
So
can
if we think
understand.
of Z as a redshift delta lambda by lambda,
Mhm.
now this quantity is different for different frequencies or what?
So
Or is it a
yes,
common redshift?
see, for FRBs, generally we have a peak frequency and then slightly like a pulse width, right? Of slight sigma. So it generally it's pretty much at constant constant, very much at similar frequency. It's not depends a lot. So
Okay.
once you, even if you apply that, your redshifted frequency, it should be reddening. So then it's also doesn't matter because it's like a particular redshift. Now
I see.
here, what we are measuring something at extragalactic, so at some galaxy and so. So we know
Yeah.
it's redshift. So that basically comes here as Z kind of.
Okay.
So that value. But
Okay,
once
all
we vary, once we need to vary like integration of redshift, that means we have to take the value from each point in the space. So it's like
Sure. Yeah.
Z0 to Z. And then,
Yeah.
but your frequency do not change as much because, I mean, it might change, but it's like one frequency which is only changing.
Okay. All right. Thank you.
So to estimate Hubble constant from FRBs, what we have done, we've considered only the localized FRBs. This is from my last year's paper. So the number of localized FRB was less. Currently it's 118. So I used, say, all the localized FRBs. That means we know their redshift from other measurements. And I plot it here. I need to estimate the DM IGM contribution that I showed. So that means I need to subtract all the other contribution. As I said, there are four parameters or four components which contribute DM, and I need this particular parameter because Mackart relation depends on this particular parameter. So to subtract all three components, we need to know their values. So in the first portion of my talk, what I'm going to consider that suppose I know the Milky Way galaxy value that also Manjari asked a few moments ago, what kind of model. So it's like any 2001 model that I used for these values. So now, what are the other two? Other two are a little bit uncertain. Hello is little less uncertain, and more or less we have an idea that Hello should contribute in between 50 to 80 parsec per centimeter cube. Whereas host is the most uncertain because host can be from different type of galaxy, different distance, and the FRB can be originated inside the galaxy, slightly outside on the galaxy, and so that's the most uncertain. It's very difficult to measure. So people generally use simulation, and one popular simulation is illustrious TNG simulation. And using that simulation, people have obtained the host contribution, some empirical formula for the host value. So in the first portion, I am just using the value from this, and then I subtract both of them. So I got the IGM contribution. And thereby I can calculate this. I have this quantity. I now know the redshift of this because I consider only the localized FRBs. So from this relation, if we know all the other cosmological parameters like omega matter and etc., omega baryon, so I can calculate the Hubble constant. So that's what exactly I did using Bayesian analysis. So I consider a likelihood function, which is like a Gaussian likelihood because it just depends on the one parameter, DMIGM. And error is all the possible errors of all the components. And my Bayesian analysis gives me a Hubble constant, which is roughly 70 kilometer per second per megaparsec, plus minus roughly 3. So this is the best what we can get for Lambda CDM cosmology, and using, if we know all three components. But of course, this is not the best way to know because, as I said, the host contribution is not known. So in the first modification, what I have done, I'm just using this relation, just subtract Milky Way and the Hello contribution and write the other two components in terms of its average. And this average I know from the Mackart relation. So now I can estimate both Hubble constant and kind of the mean dispersion measure of the host. And if I substitute, I use the similar likelihood and estimate both of them together, I can obtain a Hubble constant here and the mean dispersion measure of the host contribution. And you can see mean dispersion measure of host contribution gives roughly around 100, slightly over 100 per centimeter cube. And Hubble constant slightly shifted to around 75 here. But the error bar is still remains like plus minus 3. But it still indicates that Hubble constant is more towards the late time universe cosmology. So it's kind of over 70 kilometer per second per megaparsec value. So this is with just some averaging quantity, but I don't want to do average anymore because I now want to do this these values more of probabilistic way, so that they will be more accurate to or more precise in terms of the cosmological parameters. So to do that, I use the simple Bayes formula that we learned earlier in school. That suppose we have three random variables, x, y, and z is equal to x plus y. Then the probability distribution of z depends on probability distribution of x and y where y depends on z minus x dx. So to apply this in our formula, we have now this excess contribution, which is IgM plus host. I can now use this formula and we can get a probability distribution of this excess in terms of probability distribution of IgM and the host. So, just substitute here and I obtain this particular probability distribution. So now what kind of probability distributions these are? So this is another uncertain quantity. But most papers after basically Mackart, they have done some simulation and showed that they should follow this. I mean, they are mostly following this kind of relation where the IgM contribution goes like looking like a Gaussian, not exactly Gaussian, but somewhat similar to Gaussian, whereas host contribution goes as a log normal distribution. And then the parameters, you have all these other parameters like mean, etc. are there. Of course, you can change all this contribution. I mean, all this formula, like you can consider some other distribution. So then you will have different parameters in the model, basically. So if I now use this and I use basically this, I mean, what are the values of these parameters like beta 1, beta 2, C0, and etc. So different papers have done some simulations and they have proposed different values of them. So I substituted 4 of them. And you can see mostly they agree, doesn't matter what kind of value, except that one model, which is slightly off due to some other reason. But mostly they are in agreement. And once I now vary this likelihood, I obtain this particular plot. And you can see now I'm getting roughly a value of 73, very near 73. And my error bar also decreases. Initially, remember, my error bar was plus minus 3. So it's tough to say whether it is early time universe value or consider, I mean, it's agreeing with the late time universe, but here it's very much agreeing with the late time universe because now it's agreeing with the 73 and the error bar is also quite small, like around plus minus 1.5. So once I use this probability distribution, so my Hubble constant agrees, Hubble constant from FRBs under Lambda CDM cosmology agrees with the late time universe cosmology. So here, while doing this, I have used the probability distribution of IgM and host, and assuming I know the halo. But as I said previously, halo is also not that much known. It's also a little bit uncertain. So if I now put the halo on the right-hand side, I can just write this integration, this Bayes theorem into integration rather than one. And then also I can estimate the Hubble constant. And you can see it doesn't differ much. It's still near 73. The error bars also do not improve significantly. So like halo contribution, like halo uncertainty is not, that's why it's very much considerable. So we can still work with the previous model where we just need to consider the uncertainty on host and IgM. But all this model basically agrees that the Hubble constants should follow the late time universe cosmology.
Sorry,
So whatever, yes, sure.
So in the previous one, you had the left-hand side, which was what the excess is. It's like DM.
This one or?
Like the top line there.
Sorry. Yes.
Yeah, that means excess or what?
Yes, I just wrote it. I mean, you can write it excess. Yeah, it's like access to our Milky Way. contribution, something like this.
But
That's
that should be zero, right? I mean, like you have to match the observed dispersion, if I understood correctly.
yes. So no. What I mean to say, see, observed
Yeah.
dispersion is coming here.
That's
I
right.
know from my 2000 electron distribution model, my Milky Way contribution and some halo contribution. So
Yeah.
whatever I'm getting, so this minus this should give the other two contribution, right?
That's
I mean,
that's
this
an
should
equal.
be the
Okay, all right, okay.
yeah.
Got it. Okay. Yeah.
Okay.
Yeah, so if I understood correctly, so your ability to measure H naught
Mhm.
is like contingent upon modeling the DM properly. Is that correct?
DM, I mean, each DM components, yes.
Each DM component.
Yes, like primarily host and IGM. That's the main point. So,
Yes.
but basically this, the formula that I have written in the previous slide, that log normal and so it's from that Mackart paper. So before Mackart, that Nature paper came, people use some other distributions also. So then you can also estimate something else. But since Mackart has done in that way, using that illustrious simulation, so people are more prone to use this particular two distribution functions. Only thing they now look at what are the values of the parameters in its distribution.
So my question basically is whether it is relying on the modeling of this DM, or are there observational ways of getting these numbers?
There are both basically. See, one way we know, like as I showed also, that average host dispersion should be around 100. That some people also got from their other way of getting this. So whenever you are targeting a probability distribution, your mean should be around 100 and so. That's one fixed thing. So similarly, you can also do the other things slightly in that way.
So other way of asking this question is if I make the H naught, let's say 75 versus maybe getting 65.
Yes.
So is there some way to pick the DM so that I can get these values, or will I be driven way out of any sensible DM in order to fit 25 versus 65, or can I do it?
So see, if you want to do it for individual FRBs, you can get like individual FRB can give you any value, right?
Okay.
Because they are, I mean, you can see even if my plot here. So if you see some points are quite outlier to the
That's right.
mean value. So they might give some 65 or other side also like near 100 also in some case. But if you look at kind of an averaging that in Bayesian analysis we did, we get a very near like an averaging value, which is near this. Yes.
So the point is for the different, like FRBs, they all should have a consistent DM, which then constrains what is possible.
Yes. So the problem, yes. So why they are not matching? Of course, the values that we do not know. So either you put simulation or use some mean values, etc. So they are not accurate. Like it's some, I mean, the FRB can be inside one galaxy and outside, say, outskirts of our galaxy, even for our Milky Way. So if you look at some near the disk side, you have more material there. So your DM is high, rather than if you look at face on, they will be less. So even inside Milky Way also, it's that much different. So one galaxy, which is like at redshift 1, it's very difficult to know whether the FRB is coming from inside, outside, the galaxy is face on, edge on, what like. So it's pretty difficult to measure this quantity. And because of this, all this, I mean, deviation from the expected values occur.
Sorry, what is the y-axis here?
This is the redshift here, redshift of this FRBs.
Okay, thank you. Yeah.
Okay.
Hey, Shurajit, before we go, I have a small, means not a question. So, see, Mackart relation was long ago, means not actually long ago, but how the field is progressing. So 2020, and it was the date of year of publication, and he had data up to 19, right? So don't you think we should, is it, how logical is it to take it as God-given relation? Instead, cannot we do reverse the problem and say you take something, say you believe in early universe cosmology, and you take Hubble constant, you take the distribution around there in the, and then you, with that, you check whether this Mackart relation still holds, or we get a new better relation, and you take
So,
one
yes.
H0 from the late universe values from peak or a Bayesian distribution and see what happens so to Mackart relation. So means I'm thinking improving
Yes.
or testing Mackart relation.
So yes, let me answer. So see, this dispersion measure is column number density, so divided by redshift. So that is pretty exact, right? So now we know the luminosity distance and the redshift relation.
Yes.
That's what Mackart did. And now only the thing is this number density thing,
Yes,
right?
exactly.
And
Yes.
if I use this average number density in terms of, say, proton number density, I mean, the ionization, the matter density divided by volume, so we get particularly this relation, right? So this is
Yes.
the relation. It's coming from kind of the first principle of dispersion measure. So I don't know if we can change the form of this relation. So this form, like it's pretty, comes pretty naturally, right?
Yeah, not the form, but I think this function, if you have, and that chi,
Okay, yes, of course. So,
those
of
were
course,
his
so,
fitting function, right? Yeah.
yes. So, of course, the once I choose, of course, you can change the model, and that some people have done. So, all these models, the model 1 is from the Mackart value, but model 2, 3, they are very recent values. So, they use this, but with more number of FRBs and better simulation. So then they obtain slightly different values of C0 and all these parameters here.
Okay.
And so those values are different than the Mackart one, in fact, and more recent one.
So that gives you just very slight shift, right? Yeah.
Yes, except the one model. So this model by one Chinese group they did. So what they found, they did not consider constant values for all these parameters. They considered those values also depends on redshift and see what kind of some relation on redshift. So it's kind of little off, I found.
Yeah. So, yes. So maybe the whole thing means in the SK era we can relook at. Okay, sounds interesting.
Yes.
Thank you.
Yes. Okay. So as I mentioned, to obtain Hubble constant, we need to assume some cosmology model beforehand. I assume Lambda CDM. So what happens if we deviate from Lambda CDM? So that's what we did. So there is a very famous model called CPL parameterization, like omega 0 and omega A cosmology model, where this Hubble parameter, unlike the Lambda CDM, it picks up one sign. So it's also something like called dynamical dark energy model because this factor is dynamical. So if I now estimate Hubble constant using this particular equation of state rather than Lambda CDM, so I just choose one of the models, say model 1 or 2, I forgot which one I use, but it doesn't matter. So one of the model gives me the value here. But once we change the cosmology, underlying cosmology, you can see for different combination of omega 0 and omega m, my Hubble constant is different. So from FRB, it's pretty important that the Hubble constant that we measure depends on the underlying cosmology, and the late time universe value that we mentioned, that's only true for Lambda CDM cosmology. If you deviate from Lambda CDM, it might be something else, and that's what I'm coming now. But this is pretty important. This is the subtle difference with respect to the, say, type 1a supernova measurements, where we do not assume a cosmology even in the late time case, but here we need to assume that.
Yes,
So,
can I just ask one thing? So here, what values of lambda m and omega m and omega lambda are you supposed to take?
So it is completely unknown. So I'll come in the next in 2-3 slides later. But here I just showed that if you used omega 0 -1 and 0 is Lambda CDM, so this middle point. but I mean, if I choose something else, the Hubble constant changes. So that's all what I need to say. Now to coming to your question, what kind of values of omega, all these parameters naturally comes. So that's what I'm coming to my next next portion. So, so to understand this, what I have used two different methods. One method is same as the Bayesian analysis that I have done, but on the top of this, I've used machine learning method. So for this particular case, I have used ANN networks, artificial neural network, where kind of you have input layer and output layers, and you have some hidden layers are there. And I'll not go into the detail of all the architecture of this, but I use the PyTorch module in Python and Bayesian bootstrapping with Monte Carlo dropout for uncertainty calculation. So once I use this thing, so what I have got, so I have, now I have 114 data. This is like 2 months ago. So I have more FRBs now. So once I put this data to learn what the machine learning will say, so all this data are in favor of this rate curve. And I just plotted top of this Macat relation, and you can see they are very much in agreement. So this machine learning curve is quite in agreement of this Macat relation, but it's I mean, not exactly overlapping, slight difference is there, and that's what I'm going to discuss now. So this, so the takeaway from this slide is that this machine learning curve
I have a question.
yes.
I actually have
Yes.
two questions. One is that in the analysis, how do you take care of the horizontal error bars? That means that so error bar is okay. So the error bars are only in the horizontal. That means you are plotting it as like you should y versus x. Is it?
Yes. So okay, let me explain to you. So I did not plot in the x-axis, y-axis error bar. That's because the FRBs are very much well localized. So they do not have much error bar. They are pretty small compared to the redshift values. So that's almost equal to 0.
I understand. Actually, I was since usually people use vertical error bars. That is in the y-axis. It is a other convention that you have taken. The second question,
okay, yes, okay, got it, yes.
Okay, so now in the machine learning, so when you are using this neural networks, how are you incorporating the errors in that
Okay,
network? Yeah.
sure. So what I have done, of course, if you do not use error bar, you have like one line for now. Suppose just one line something. Now once I put the error bars, I have used in two different ways. One is Bayesian. So what I did, it's like every time I run the code, like training or validation purpose, I basically choose not only this point, I choose any points in between these values. I choose a Gaussian-like function here with mean and standard deviation. And then I choose some values in between this. So every time I'm running, I use that value for X and Y is fixed. But again, then I have used bootstrapping. That means every time I run the code, that does not mean that I need to use all the points. It's like, say, 80% or 70% points that I've used. So that's bootstrapping. So that gives me uncertainty. And then something called Monte Carlo dropout. That's basically also similar to that, how much of that validation we want to use. So what percentage we want to drop. So it's like the neurons. So if I use Monte Carlo dropout, say MC dropout equal to 0.1, that means 1% of the neurons will be manual or automatically randomly turned off. And then what's the value? So in this way, I have used all three methods possibility to estimate the uncertainties here.
Okay, so all three methods, they actually combine in a particular run to get that particular band over around that line. All three are included.
No, it's from after lots of runs. I've run it for 1,000 times. So it's like combination of every run, basically.
Okay, it's a combination of every run. So are you sure that these combinations are additive so that you can just run them together and so that you can just combine them?
So it's not additive. So first of all, see, so Bayesian portion, I don't know. So it's like at the beginning. So when I'm putting in the input layer, so I'm using the Bayesian portion. That means some values in between this error bar. So now MC dropout comes in the hidden layer calculation. It's like when I'm calculating the hidden layer, that MC dropout method comes. So after doing this for one run, I'm getting one value. And that then I'm using basically bootstrapping. That means how much percentage I want to use of this data points. So in the next run, again, I'm using Bayesian. In the hidden layers, I put MC dropout, and then at the last, I put bootstrapping. So when I'm collecting all of them, it's like collecting all the bootstrapping one, which is obtained after implementing Bayesian and MC dropout at the beginning.
Okay, but okay, so let us, okay, now going back to the very basics from here.
Mhm.
Since you have a error bar, what is the loss function that you are using?
Loss function, I have used a weighted loss function for here. So it's like generally you have y prediction minus y square by
Yes.
this, but also because these error bars, they look like pretty equal, but they're not. I mean, slight difference. So I put that weighted square also. So larger the error bars, so it's 1/weighted square. So larger the error bars, lesser is the credibility of that point, kind of.
So that is the basically the chi-square, right?
Yes, chi-square, yes, of
Okay.
course.
Now, if you are using chi-square, then
Mhm.
you have a definition of a likelihood.
Yes.
I mean, you can, if they are uncorrelated or even if they are
Mhm.
correlated, you can, as a first approach, you can write the likelihood as e power minus chi-square by 2,
Chi-square,
right?
yes, yes. Yes.
Then since this is showing a very linear curve, you can just try to first do a linear search with the likelihood, which will be completely a Bayesian approach, and it will show you whether, and then you can see whether you need any deviation from the linear curve, right? So what
Yes.
I'm failing to understand is that why did you need a neural network for for such predictions and things like that? Because if as a first approach, if you have certain relation and if you want to know the deviation from the relation, you could have added a simple function. If you have seen that there can be certain type of
So, oh,
deviation by going to the
oh,
residual curve, and then you could have checked that whether it needs certain deviation from the
see,
McCarthy.
okay. So it's see, there are two things. One is that this is not exactly straight. So there is slight deviation here because I'm going over one redshift of one. So this is not exactly straight line. And the second point is that I have not used this McCart relation anywhere to calculate this machine learning predicted curve. The machine learning predicted curve is purely on the data. I just plotted it here just to see if my machine learning outcome plot is matching, I mean, how closely it's matching with the McCart relation. So McCart relation didn't go anywhere in my analysis. It's
No, that
just
I
the
understood.
comparison.
That I
Yes.
understood. But my question was that, let's say you have McCart relation now, whether it is deviating, whether the data demands or the observation demands any deviation from the McCart relation. A simple thing is that one can just see whether you need certain running on that particular relation, running of that particular slope that you are that McCart relation is showing. That one can search, and if that turns out to be the running turns out to be consistent to 0, then we can simply say that we do not need any deviation from the McCart relation. For example, even if it is not very linear, if you add running, it will not also be linear in that case. But if it
Yes.
is not linear, it shows that your prediction from the neural network is completely consistent with the McCart relation, uh, given the error bars that you are trying to generate. And also, at an additional point, what I understand that from the machine learning, all these networks actually adds on the uncertainty. And since it is allowing a plethora of possibilities, that sometimes you are actually um, killing the predictive power of that particular data set, because you are allowing lots of freedom. And that is what my concern. So one can simply use a one parameter extension, or can, for non-parametric case, one can use a Gaussian process. The question is
Oh,
that,
yes. Gaussian process is a possibility that I'm currently doing. Of course, here I have not
okay,
used that Gaussian thing.
yeah, that is
So,
my thing, is that
yeah.
without going to the step by step, whether adding this neural network, did it which actually is known to inflate the error bars, did it give any extra insight without starting from the first principles and things like that, going to the completely machine learning regime and AI regime and things like that? did it give you any extra handle on your analysis, etc.?
Um,
Other than the conventional approaches.
Okay, so that one, of course, I need to try the way you said. That's a different thing. But I think for that, I need to specify the Mackart relation. That means I need to specify the Hubble constant at the beginning. Because
Not
Mackart
really. I
relation,
mean, you can use a Gaussian process as well, and you can try to see that whether there are any what is the band, error band, which is addressing the data, and on top of that you can plot the Mackart relation just like this one to see whether it is consistent or not. All right.
Yes, of course, like Gaussian process, as I know, I'm not an expert on that, but as I know that Gaussian process is a different approach than this ANN thing, right? I mean, to predict some deviation. Like here also, I obtain the full curve and then do the Gaussian process is kind of the deviation, how much it should go from the mean or the average values.
Yeah, that is true. I mean, what I'm
Yes.
saying is that it is a different approach, but neural network is sometimes known as a method that increases the error bar significantly. That is one of the flag for me. That is why I asked you why you needed to go to the AI regime. Even if you did not start with the Mackart relation, you could have started with simple straight line and see whether the straight line is a good fit. Then go to the adding more corrections to the straight line at low z or high z and things like that. Just a single parameter extension and things like that, which is much easier to address and easier to understand. Okay, so that is my question is that if you had those results, then we could have seen that whether neural network is giving you something more or not. Okay.
Okay.
Or it is worsening the error bars or not. All right.
Okay, sure. Yes, I can try that. Yes, that method I can try. Yes, sure. Yes.
Yeah, sure. Please proceed.
Yes, sure. So now I have this machine learning predicted curve. What I am going to now do to find out the Hubble constant from this Mackart relation. So as you can see, my machine learning has predicted me this particular value, some value for every redshift. And I have this here. So let's assume Lambda CDM for now. And then I can estimate Hubble constant literally for every value of redshift. So it's like what I said at the beginning. One is coming from the observation, one is coming from the theory, the Lambda CDM in my case. So if I now do this, I can literally obtain the Hubble constant at every redshift value because it's like a continuous relation, something like this. So what I have done, I estimate Hubble constant at every redshift value from 0 to 1.4, where I have all the FRBs. And I see a deviation, a deviation on the Hubble constant. Now this deviation is slightly opposite if we assume omega b equal to constant from dark energy survey or omega b h square equal to constant from other thing like Deci, or Planck, etc. So, but there in comparison, I'm not talking in detail, but you can understand that the independent parameter here is if you take out this H0 here, it's omega b into H0. So that's basically kind of estimating. Now from omega b H0 to estimate Hubble constant, you can do omega b H0 by omega b. And that's give me this all the top curves, or you can estimate Hubble constant like omega b H square by omega b into H. So those will give me the bottom curve. It's just like inversely proportional to each other. But the more important point is that for a particular value of Fij, etc., consider, you can see there is a significant deviation on this curve, the continuous curve. Now to validate, because these I obtained from the machine learning, I want to validate this from the Bayesian analysis as well, that what does Bayesian analysis say? So to do that, I wrote in this equation, basically I divided all my FRBs in 3 bins because I do not have lots of FRBs, only 110 FRBs. So I just use 3 bins, roughly 38 FRBs in every bin. So then I can write this expression in this combination like 0 to Z1, Z1 to Z2, and Z2 to Z3. And let's assume the Hubble constant is different. Had it been the same, it will come into this same expression. Suppose it's different, then I vary these 3 quantities in terms of Bayesian analysis and try to get the values of H0 and H02, H03, and that's what I plotted here. So No, so it's omega b constant at this. So you can consider any of this case, and you can see it's also showing a significant deviation with the increasing redshift, the value of the Hubble constant. So, and this is just those points, that H0 and H02, H03 for two different cases. But that means the Hubble constant itself is changing with the increasing redshift, which is against our intuition of lambda CDM thing. Suppose I go to a different model like omega 0, W0 WA model, and I try to see whether that variation of Hubble constant can be reduced. And this chi-square is something like how much those 3 points, or how much that the lines are kind of straightened out in alternate cosmological model. And from this, I found that for omega 0, omega A, for this particular quadrant, you can literally obtain some values here which are very much inconsistent, that Hubble constant is constant across all 3 beams or across all the redshift, whatever method you use. So,
Sorry, I did not understand this plot. How does your last slides contour results in these contours?
So, okay, so suppose, let's consider the machine learning because they are complement, or you can consider the contours also. So this curve is only for lambda CDM because I had to use lambda CDM here. Suppose I now deviate from lambda CDM. Let's estimate H0 and H02, H03, and let's see if this curve is straightened, or these 3 points are how much it's straightened for different value of W0 and WA. So if it's getting straightened, I defined one reduced like a chi-square or reduced chi-square things, where it's like kind of how much it's straightened. If it's exactly straight, so this is basically 0, so you get somewhere here. So that means for those particular W0, WA value, my Hubble constant is a true constant throughout my redshift, at least from 0 to 1.4.
But W0, how does W0 and when you are doing the machine learning in the last plots, you are just getting constraints on, here you are getting H0 as a function of Z. So,
Yes.
okay, so you are now translating so given a particular H0, which model of dark energy, assuming the dark energy equation of state to be CPL,
Yes.
what will be the constraint on W0 WA? Is it?
I would say it's opposite. What I mean to say, once I need to estimate this, I assume lambda CDM at the beginning and try to see how Hubble constant is varying. In the next plot, what I'm trying to find is basically how, if I change my Hubble parameter here, so denominator we have that FZ thing here, and now I'm estimating Hubble constant. So I have the machine learning curve, predicted curve, but my Mackart relation will be now slightly deviated depending on what kind of denominator, what cosmology I'm using. So then I'm trying to say for that particular W0, WA, my H0 is a true constant. So it remains constant after, throughout the redshift. So that's
Sorry,
what
H0. Okay, no, I think there is a confusion in terminology. H0 is Hubble parameter at Z equal to 0. So H0 does not change with redshift or anything.
So
H0
that's what,
is,
so
yeah.
yes, so that's what my point. So when I told you about this expression, I said that even in other cases also, suppose so this model says that H0 is a constant, right? Even if you change your redshift,
No, it is
H0
nothing to do
cannot,
with the model. H0 is a value of Hubble H0. H of Z is a variable quantity. It is a
yes,
Hubble parameter. But
yes.
H0 is a Hubble constant. That is the value of Hubble parameter today. So
Yes,
H0 cannot be variable.
So yes, that's what that's the assumption of lambda CDM, right? Because once we solve, we obtain Hz is
That
proportional
is
to
not the
these
assumption
things.
of the lambda CDM. That is a normalization. For example, the universe has A equal to 1. A means A0. That scale
Yes.
factor today is 1. That is not the assumption of the Hubble, not the assumption of the lambda CDM. That is our normalization. Similarly, H0, okay, H0, we are calling it to be something. It is a constant. Some people use this h of small h of z as h of z, capital H of z by small, capital H of z divided by H0. That means that at redshift 0, the small h of z is always 1. So this is how you normalize. It does not matter what model you choose. For example, the sum of all omega is equal to 1. Okay, this
Yes.
is a normalization that we are.
So what my point is, suppose you can, okay, what you said is correct. Suppose now I go to redshift of other redshift, say redshift 1. So this formula will still be valid. Hz is this formula.
This is
So
a
if you,
formula of h of z, not h of 0.
yes, I'm saying this is valid across all the redshift, right? I
Yes,
mean,
given
doesn't
a
matter
W
what
of
other.
z. Yes, given a
Yes,
W.
yes, for particular thing. So this is valid for all the redshift. So now suppose I'm estimating it for redshift of 10, let's say, or redshift of 1, let's say. So my right hand side, this exponential factor will change. I mean, it will come from 0 to 1 with some value. And left hand side will also change. But my Hubble constant will not change, right? Because that's a true constant, as you said. It's a constant.
Well, this is an equation of h of z. Okay, this is the very simple equation.
Yes,
H0 is constant by design, by the way we are doing mathematics. We are saying H0 is constant. Because the today's value is constant. This is, I mean, no one can change it. It is just a constant.
yes,
And because we are starting our observation from today, so today we are here. From when
yes,
we see back in time, we see the evolution. Okay,
yes.
and if you are saying that some y equal to some constant time x, if x changes, definitely y will change, right?
Mhm.
Because
Yes,
c is the constant, is a constant. There is nothing to, I mean, we cannot get any extra
yes. So
information from the right hand of the equation.
yes. So that's my point. If this is a true constant, it cannot change with the redshift. It has to be a constant.
It is defined at redshift 0. It is not defined at redshift 1 or 2. It cannot change with redshift. That particular sentence does not have any meaning. If you are saying H0 cannot change with redshift, it is not even a proper sentence, because H0 is not defined outside z equal to 0. Am I clear? When you are saying that it should not change or something like that, H0 is not even defined outside z equal to 0.
Yeah.
Is it clear?
Yeah, sure. Same.
Yeah.
Surajit, Dheeraj,
Yes.
sorry. So you have finished 1 hour. So you have
Yes.
15 more minutes. You can continue.
Okay, so then
Yeah,
I will
Dheeraj,
I'll discuss this later. Yeah. Fine.
yeah, so would I suggest that because I
No,
understand.
definitely. Please proceed, because this is
Yeah, maybe
this,
you and Surajit can discuss. I think maybe some terminology difference. Probably you people can discuss offline to
sure.
understand each other.
No. I would not. I
Yeah.
didn't want to stop, but because H0, the definition is something that we got mixed up. So that is why I was
Yeah.
trying to understand what is the, because
Mhm.
otherwise I would not able to understand the next part. So anyway,
Mhm.
so I think there is some terminology differences
Yeah,
here.
so
So
maybe
Surajit, please proceed.
yeah.
Okay. Okay, so I'll just quickly wrap up. So, okay, we'll come back to this, but what I get for, say, this particular quadrant, that H0 turns out to be constant, and this is pretty much similar that what CMB-based surface also gave, that omega W0 greater than -1 and WA less than 0. So that's what I wanted to say. So I'll now skip all the other thing that what are the other applications of
Sorry,
FRBs that, yes.
about this previous plot. So a pure cosmological constant would be what? Omega naught, W naught is -1, is it?
Pure cosmological constant means
Just lambda, like no
oh
varying. Yeah.
yes. So these
No,
are
in the next
constants. So
plot that you showed,
yes,
yeah, here you have W0 and WA, right?
yes. W0 and WA I fix for different combinations. So for each combination I get one WZ. So I get
No, but
FZ.
what is
So
just a cosmological constant would be what? W0 is -1 or what?
No, they are
W?
varying. They are varying. Like cosmological constant mean, are you meant to say the cosmological constant comes in the Einstein equation, that capital lambda?
No, W of Z is a varying, dark energy component, right?
Yes, yes.
What is the limit that I should take for a pure cosmological constant, a constant vacuum energy, lambda?
No, here it's basically saying is that, so for lambda CDM, it's -1, WZ is -1, and this is
That's what I'm
0.
asking. So for just
Yes.
like a fixed cosmological constant, it's W0 is -1.
Yes,
Is that
yes,
true?
and yes, and WA
So what
is
am I
0.
supposed to read from this, plot on the right though? That is like the best value is 0, is it? W0 equal to 0.
No, the best value is here, right? I mean, the lowest chi-square comes out here. So best value is W0 is 0. Yes. Oh, okay. W0 and WA
Yeah, now my
is somewhere.
puzzle is why
Yes.
is it like not like consistent, at least with -1? It looks like it is dragged quite a bit away from
Yes.
cosmological.
So it's, I mean, it's not only from my result, from the constancy of H0, etc., I showed this, but this is also proven from the Deci result or Planck result also, that if you put W0, WA, you get slightly the quadrants or the ellipse on this particular side.
So like what level is -1, like not favored now?
I mean, that I forgot that what sigma.
No, from your like
oh,
roughly.
For me, it's like just, it's not very much deviated. So W0, WA gives me slightly over 1, and chi-square 1 over 1, reduced chi-square greater than 1 is not that great, but less than 1 is.
The red and the blue are actually 1 sigma, 2 sigma, or?
No, it's not 1 sigma, 2 sigma. It's just the color plot of this thing.
Okay.
So if I just take your best value and then ask by how much is it like different from -1, W0 equal to -1, would you be able to quantify that? Like how?
I should, yes, I should be able to quantify, but I did not calculate it as of now.
Roughly? No? Okay, all right.
It should be more than 1 sigma, because 1 sigma, within 1 sigma means it should be coming, this point should be within the contour, but it's deviating from 1 sigma, so it has to be greater than 1 sigma, that's sure.
Okay.
But exactly what's the value that I have not.
Okay, all right, please continue, yeah.
Yes. So I now skip all the other contribution of FRBs. So I'm just coming to my summary, the future slide. But as I said, I did FRBs mostly last 3 years and did some cosmology, but also with the other things. But other topic that I have, I am doing parallelly FRBs on white dwarf. So I have simulated white dwarf structure in GR or in modified gravity and the gravitational waves from there. Also, some topics are quite overlapping, like constraints, fundamental constraints, or constraints on constants. So those are this, and then identifying also some use dimensionality reduction technique to identify magnetized white dwarf or stability of white dwarfs, and some other topics which are related to these topics like modified gravity, etc., but in black holes or neutron stars. So in way forward, I am currently a member of the HIREX collaboration, which is 256-2024 DCs that's being planned, which will be operating at a 400 to 800 megahertz. And currently 2 DCs have been planned, but once all the DCs will be planned, it will be looking like this. It will be in South Africa. And this is a prototype. So the scientific goal of HIREX is that it can detect lots of pulsars and FRBs on this due to these frequency rates. But it can also detect, this is the main aim of that. It will detect hydrogen H1 21 centimeter line from BAO. And because of this 400 to 800 megahertz, it can go up to 0.8 to 2.5 redshift. And once we get this in the sky, we can cross-correlate with other cosmological surveys and make large-scale structure of the universe. And looking at this frequency, it's very similar to CHIME, except the design, but it's on the southern hemisphere, and CHIME is in Canada in northern hemisphere. For FRB, the predicted number is that once 256 DCs are planned, it's expected to detect one FRB every day on average. So this is my this is the sky coverage of HIREX. HIREX will go roughly from this 0 to minus 60 degree, which will have some overlap with time, but with other cosmologies like DC, etc. And this is what we have predicted for HIREX, that HIREX 256 can go up to around redshift of 2, but majority it will detect up to redshift 1. And if we have more dishes, it is going to other side. It's not as great as time or its upgraded version in core, but it is still on the southern hemisphere. That's the best we have. So some future aspects that I'm currently working on, that as I said, all the FRBs, I need to assume some cosmology beforehand. So if we can use some method or something to understand cosmology independent modeling of FRBs, I mean to understand some other parameters, and then to understand FRBs to other physics like mass of graviton or action like particles mass. And then whether we can cross-correlate, or we can obtain FRBs and GW events together and neutrino events from just one particular site. Similarly, for white dwarfs, I'm using data simulation, etc., and try to understand type 1a supernova, physics of type 1a supernova, and if we can use it for precision cosmology. Also, I've recently joined one project on cost research section project, which will be detecting, which will be doing research on pulsation and white dwarf astroseismology. And also currently I'm working gravitational waves here in the Warsaw. So I'm using the LVK data, the recent release of O4A and B. And whether we can, I have already used it to classify some outliers, but whether we can do some other cosmological parameters or binary evolution study. So the conclusion is that, as I have shown in the second portion, that Hubble tension might be an artifact or might be a limitation due to the Lambda CDM framework. But the other aspects are that FRB provides stringent constants on Hubble constant. FRB data and white dwarf data can independently constrain other parameters of cosmology. And constraints, of course, as of now depends on Lambda CDM or the underlying cosmology. And for white dwarfs also, if we do, it depends on underlying gravity theory. And in future, if we can detect gravitational wave and neutrino from FRB sites or from white dwarfs sites to understand some better mechanism like magnetized white dwarf or understanding the progenitor mechanism of FRBs. So thank you all.
Thank you.
Yeah.
If you have any questions, you can ask.
Hi, Surajit. Regarding FRB and axion-like particles,
Yes.
do you think that FRBs are the best proof for the axion-like particle mass constraining, or in future, what type of probes will be competitive, or can you just give an overview? Like,
okay, so I forgot to plot. Yes, I forgot to put the plot here. So already people have put constraints from pulsars. And pulsars are basically within our galaxy, whatever detected mostly, right? So we just try to use this idea just to generalize. If we can extend this idea to FRBs, something similar to pulsars, and then what will be the constraints? I have some preliminary results which shows that it improves slightly bit, mainly because FRBs are a little far, and that's the main reason. But of course, as I mentioned, one thing is that those are not the best constraints or the best values in the literature, but those are some constraints that the FRBs or pulsars basically can put on these values.
Okay, anything else?
Yeah. Hi, Surajit, can
Yes.
you tell us what is the status of HIREX? When is it coming?
So, initial plan was that HIREX 8 dishes supposed to be completed by this year, but I don't think they are going to do. But once 8 dishes are coming, so they will start doing proper observations. And right now they have just some experimental run, etc., but nothing has observed.
So,
once
a few dishes are already there?
Yes, these 2 dishes, the image of the 2 dishes that's already dead, but they did this like 6 months ago only.
Okay.
So after that, I don't know why they did not put more dishes as of now.
Yeah. So will they be able to Because SK is working on full-fledged, right? So
Yes.
will Hyrax be necessary, or they will drop the proposal because Meerkat is already there and it is being
I
absorbed in
don't
the
think
SK?
so. I don't think so because the operating range is different with the Meerkat, right? So maybe that's why they want to
Yeah.
still keep
Yeah,
with
but
respect to Meerkat.
when Meerkat is, because SK will come in 33, right? And
Yes.
this is the within the SK mid. So yeah, I
So,
don't
I
know.
mean, ideally they were supposed to, I mean, their initial plan was 256. This was already commissioned. So they
Mhm.
initially planned to have it by within 2-3 years or
Yeah, that
so.
would be, yeah.
But that's getting delayed and delayed for
Okay.
other reasons.
Because
But
yeah, it
yeah.
would be good if means until SK comes, if people could use Hyrax, right? As
Yes, of
something
course.
complementary. Yeah. Okay.
Yes.
Okay.
But yeah, yes, as of now, this is the status, unfortunately.
Okay.
Anything else?
Just a question on that W0W or A plot that you showed.
Yes.
This one, yeah.
Yes.
So this one, you are saying that it is evidence for changing W, right, as a function of Z.
I mean, yes, of course, this is, I used already. That means I used one dynamical dark energy model, which says that my dark energy equation of state is changing with the redshift.
Yes.
So
And
in
so
that
I'm
case,
still trying
we
to get a
get,
sense at what level is it, deviation from -1. Some W equal to -1.
okay, yes, that you can calculate for this particular case. Say this one comes at omega W00 and WA is -2. So you just need to substitute this. And for lambda CDM, this is -1, this is 0. So then you can calculate some, I mean, all this. But definitely, it's, as I said, it has to be more than 1 sigma for sure. But that number
Okay.
I need to calculate.
And is this consistent with the DESI result, or how does
Yes.
this?
Yes, for DC result also, if you see I mean, the thing is different. I mean, the physics, or what I mean to say, the data is different. But once they try to fit that data with this CPL parameterization, W0WA, they also find their best fit contours. Not exactly for this is their best. They got somewhere slightly on this side. Their contours look like here, basically. So they also, but kind of the quadrant is the same, that W0 greater than -1 and WA less than 0 agrees with their CMB data, and so as in my case.
So here too, this one, is an agreement with the CMB data, I guess, right? The omega
Yes,
m,
yes,
and then omega lambda that you take.
yes.
So how do you do this thing? So how do you ask whether it is an agreement with CMB or not?
So what I did, as I wanted to explain, so for this age, when I choose only lambda CDM, that means W0 is -1, WA equal to 0. I obtained this denominator in this fashion. And then I calculated the Hubble constant here. Then once I substituted different cosmology here, that means my denominator is changing. The denominator here is changing. So that will give me a different curve of this. So the curve will be like for that best fit value, the curve will be straightened. Once the curve is straightened, I say that that model prefers H0 not to change at all with respect to redshift. And those models are in better agreement with the FRB data.
No, but my question was about CMB. How do you,
Oh,
how do you
no,
ask
no, no.
whether it is in
Oh,
agreement
no,
with
no, no.
CMB?
I did not use CMB at all. I just said that the quadrant is pretty similar as CMB people also predicted from CMB observation.
No, but
One
I have
update.
to ask, is it compatible with the CMB also, right? And at what level, or is that not asked at all here? This is an independent fit to the data or what?
Yes, this is independent fit to
How
the
do I
data.
compare it with, like the H naught value that I can get from CMB or the omega matter from CMB, omega
Oh,
lambda.
okay. You mean to
So-
say in that way? Yes.
Yeah.
Okay, yes. Once you, yes. Once you get basically the constants, so then the users need to check whether that constant is matching with the CMB predicted constants, say H0. Now, for me, the
So
H0,
for you, omega matter is completely free variable, is it?
no, omega matter and omega lambda, I need to constrain because I can just constrain at best one parameter from here. I cannot constrain all three parameters together
So
just from
total
FRB.
omega is 1. That's the only constraint.
Yes, that's the only
Otherwise, omega
constant.
matter is free to change, and you can split it.
No, yes,
any
I
way you like.
fixed already beforehand.
Okay.
This I fixed. Yes, I fixed already.
But otherwise, it is free to change, is it? Without
Yes,
regard to
it is
CMB.
free to
Okay.
change, but then already there was one paper in 2018 that people have used to, the CMB and supernova, etc. Then you can actually you need to combine 2-3 different data sets. Then only you can constrain more than one parameter together. But
Okay.
only FRB you can constrain one. So either if you put some constant here, then you can estimate this. But if I put constant here, then you can estimate this.
Yeah.
Okay, on the same thing.
So
if
one
you are-
question. So if I look at this Z plot that you have, if I look at only the larger Z part, it looks like H naught is fairly constant.
Yes, it's
So
getting
is it an
towards
option?
constant.
Is it an option for me to cut out the left part and then only look at?
Yes, you might say, but generally we generally say the Hubble constant we say, right? The one we measure, that's at redshift 0, that Dhiraj also said. So that's kind of, we measure it here, what's the value here. So I just want to compare what we measure versus what's the variation in the all redshift range.
Okay, now I'm also confused. So now is it H naught that you're showing? The curve is H naught or is it H of Z?
No, it's not.
So then if I cut out the left part and then look at only the right part of this plot, I would still be measuring H naught, right?
Yes.
Is that an option for me to do because it is fairly constant there?
Yes. So that's what I wanted to
Then
explain.
will I find that there is no evidence for changing f of z?
Yes, if you take more data set and if you go higher and higher,
No. With the existing data, I just cut out, let's say, everything less than 0.5. If I just remove everything less than 0.5.
Okay, yes, then you can say they are in constant. Yes, of course. Like these points are in constant at higher redshift.
And then it is no evidence for changing f of z.
Yes, kind of, yes.
No, that puzzles me. How is it that then you have a different, because that is a data set I could consider and just like ask, can I measure H naught with just that data set?
Yes.
And I get a different conclusion.
So, if you just take one side, only the data over 0.5, you will get basically almost a constant.
Yes.
H0. Yes. So that's
and
of course
W0
there.
minus 1 and WA0 would be a good fit for that one.
Yes, perfect fit. Good fit. Yes. But once I tried to get to the other side, the lower side, it seems deviation.
And those data points are what? Like the lower part is what? Like the
lower
lower
parts
Z
are basically
FRBs,
yes, low Z FRBs. Yes.
Okay. All right.
So something like if I need to take this integration, only when I take the higher integration, all three integration contributes.
No, it
If
looks
I take
like your evidence for changing f of z is coming from the low Z FRBs, and not from the high Z FRB, right?
Low versus high. You can say the comparison low versus high.
Yeah,
yes.
and that bothers me that you are getting all of this thing for it. If I focus on just the evidence for changing f of z, that it's mainly coming from the low Z FRB.
I can explain this to you slightly in different way. Suppose I have this Mackart relation.
Sorry, I don't know if this is getting too detailed, but
no, it's fine. So you can see, for example, the Mackart relation is the blue curve. It might not be that, the difference is not well. And the machine learning predicted curve, in one side, you can see it's slightly lower than the blue curve. And on the higher side, it's slightly going upper on the other side of the Mackart relation.
Right, okay.
And that's why the difference. So if it's exactly say 7, this mechanism I plotted for 73, 8073. Now once
Right.
it's coming to the lower side, it gives me say other value of Hubble constant, which is say less than or greater than 73. And once it's going on the other side, it's basically less than
Okay.
73.
Yeah, I
something
think
like
the
that.
way to reconcile this is, I think your statement is that the evidence for changing f of z is very mild, right? It's not a very
Yes.
strong, right?
It's not very strong. It just surpasses this 1 sigma level. I mean, you can see
Yeah,
here,
okay, all
it's
right.
not completely, I mean,
Okay,
very much
maybe
diluted.
that
but
will be fine.
yes.
Yeah, that's right. Yeah.
Yes.
Okay. Yeah, thank you.
Okay, let's thank
Surajit,
Surajit.
just one minute if I
Oh,
can
you have one
ask.
more thing? Okay, sure.
Yes, because I was trying to ask when Srihari asked this regarding the omega matter, when you said that you have fixed the omega matter, right? Just a clarification is needed. So that means that if you make the omega matter free or use a like a Planck prior on omega matter, then your constraint on W0 and WA will relax further, right?
Yes, yes.
Then it can even -1 can even come inside the 1 sigma.
Yes, yes, of course. That I
Okay.
tried actually. Then what happens? All my cards, it doesn't look like an ellipse. It's just like a big.
Even
And as you
even
said,
with the
yes.
even with the omega matter Planck prior or keeping omega matter completely free.
Completely free.
Oh,
Free. I
completely
mean,
free, I understand. Completely free, I understand.
yes, yes, yes.
Yeah.
I mean to
Because I
say
was
free.
thinking if you are,
I mean free 80, free omega method. Then it
yeah,
doesn't constant. Basically, it's
I
just a
understand.
big
I
contour.
understand. I understand. Thank you.
Yes.
Thank you.
Okay, okay, let's thank Surajit one more time.
Okay, thank
Okay,
you.
thank you, Surajit.
Bye.
Yes, thank you very much. Yes.
Okay,
Bye.
thank you. Bye-bye.
Yes. Bye.